Hello everyone, in today's video we are going to see about embedded Linux development from toolchains to target boards. This presentation walks you through a complete workflow for building and deploying embedded Linux applications. Let's begin. A little about ourselves. We are Krishworks Technology Innovations, a leading provider of custom IoT solutions. We specialize in working with microcontrollers, sensor integration, and toolchain creation for embedded systems. Our solutions power real-world applications across various industries like education, mobility, agriculture, and smart infrastructure. So, why embedded Linux? It's open source, cost-effective, and highly customizable. You can tailor the kernel and services for limited hardware. With a rich ecosystem of drivers and libraries, and industry-wide adoption is ideal for powering IoT and embedded systems from wearables to industrial machines. Here's a quick look at the roadmap we are going to follow. Step 1. Choose your target device. Step 2. Create a toolchain. Step 3. Develop and compile your application. And finally, Step 4. Test and deploy in an emulator or real environment. Let's dive deeper. What is a toolchain? A toolchain is a set of development tools that convert or cross-compile your source code to run on a target device. It includes 3 core components: a compiler to translate code, a linker to generate a final executable, and runtime libraries that provide core functionalities. Types of toolchains. There are 2 types: native and cross toolchains. Native toolchains build software on the same hardware it runs on, like developing directly on a Raspberry Pi. It's simple but slow for low-resource devices. On the other hand, cross toolchains let you build on a powerful host PC and run it elsewhere, like on a BeagleBone or Raspberry Pi. This is essential in embedded systems where resources are limited. Why are toolchains so important? 1. Cross-platform builds. Compile on PC, run on ARM. 2. Build entire systems. Kernel, bootloader, and root file system. 3. Debug with tools like GDB and profile with gprof. 4. Maintain consistency using a single toolchain through crosstool-NG. Creating toolchains with crosstool-NG. Crosstool-NG is your best friend for creating cross toolchains. It's open source, menu-driven, and automates the complex tasks of fetching, configuring, and building compilers for your specific architecture. It ensures consistency across your entire embedded Linux environment. Installing crosstool-NG. Here's a quick snippet of the installation process. You can feel free to take a screenshot of this. So first we'll have to clone the crosstool-NG repository from the GitHub. Then change into the clone directory. Check out the specific version tag, that is 1.24.0. Then generate the configure script and add a build infrastructure. Configure the build to install in the current directory. Compile the crosstool-NG binaries. And then finally install crosstool-NG into the current directory. Let's move on to the next part. Introducing QEMU. QEMU is a virtual machine emulator. It lets you run code built for one CPU like ARM on another, like x86. This helps you test builds without actual hardware, saving both time and cost. Building toolchain for QEMU. Here's a snippet of building the QEMU specific toolchain using crosstool-NG. First, we'll have to clean any previous configurations. Next, select the generic ARM target for QEMU. Also, optionally we can customize the configuration. Then for the build command, use this and then list the contents of the toolchain directory to verify the installation. What does a finished toolchain look like? We'll get compiler binaries prefixed like ARM-unknown-linux-GNU-EABI, a sysroot with headers and libraries, and a bin directory to add to your path for easy access. Verifying cross-compiler setup. Verify your cross-compiler by running version to check the build. Here's a snippet to guide you. Cross-compiling a program. Let's walk through compiling a sample C program. Step 1. Write your code, a simple C program with Hello World. Step 2. Compile it using the cross-compiler. Step 3. After compiling, we have to verify the binary to make sure it's for ARM, after which we can run on an emulated environment QEMU. Step 4. Run the cross-compiled binary using QEMU. This gives the output of program. Moving on to the next topic, BeagleBone Black, a target boards. It's an affordable, open source board running ARM Cortex-A8. It boots Linux in under 10 seconds and connects via USB in 5 minutes. You can expand it using capes, making it ideal for prototyping. Building toolchain for BeagleBone Black. Clean any previous configurations. Select the generic ARM Cortex-A8 target for BeagleBone Black. Optionally, we can customize the configuration. Then for build, use this command and list the contents of the toolchain directory to verify the installation. Here we are seeing how a toolchain looks after building it with crosstool-NG. In the next slides, we'll see how to use this toolchain with a practical example targeting the BeagleBone Black board. So verifying cross-compiler setup. So verify your cross-compiler by running version to check the build. And again, you'll see snippets on each slide, so feel free to pause and take a screenshot. Cross-compiling a program. Step 1. Set up your configuration using C program. Step 2. Use the below command to compile the program for an ARM-based system. Step 3. Verify the build. After compiling the program, you can verify that the binary is correctly built for the ARM architecture using the file command. You can now run this on a BeagleBone Black with ARM Cortex-A8. Step 4. We can now deploy the cross-compiled binary to the BeagleBone board. Next, we have the popular Raspberry Pi 4, a target board. Originally from the UK, this affordable SPC is compact, powerful, and supports a wide range of use cases, from programming to IoT. The next slides will guide you through customizing a configuration, building a toolchain, compiling a C program, and running it on the Raspberry Pi. Building toolchain for ARPi 4. Clean any previous configurations and select the ARCH64 target for Raspberry Pi 4. Customizing ARPi 3 configuration for ARPi 4. To start customization, open the menu Config for crosstool-NG and then make the following changes. Go to Paths and Miscellaneous Options to render the toolchain read-only and change it to false. After that, go to Target Options, select Emit Assembly for CPU and change Cortex A53 to Cortex A72. Next, go to Path Toolchain Options and then to Tuples Vendor String, change ARPi 3 to ARPi 4. After customization, let's build with the following command and then list the contents of the toolchain directory to verify the installation. Verifying cross-compiler setup. This command outputs the version of the cross-compiler, ensuring you are using the correct version for your build. Anatomy of a toolchain. Use this code to understand and use the toolchain. In the next 4 slides, we will see how to use this toolchain with a practical example targeting the Raspberry Pi 4 board. Cross-compiling a program. Step 1. Create a new file named Hello World C with the following content. You can refer to this snippet. Step 2. Use this command to compile the program for the Raspberry Pi 4. Step 3. Verify the binary. After compiling the program, you can verify that the binary is correctly built for the ARM ARCH64 architecture using the file command. You can now run this on a Raspberry Pi 4 with ARM ARCH64. Step 4. We can now run the cross-compiled binary on Raspberry Pi board. As we reach the end, let's quickly recap the key points we have covered so far. At the heart of embedded Linux development is the toolchain. It enables us to build architecture-specific software that runs seamlessly on devices like Raspberry Pi and BeagleBone. We use crosstool-NG because it simplifies what would otherwise be a very complex process. It helps us generate consistent, reliable compilers tailored to our target boards. Next, QEMU plays a crucial role by letting us test our code without the physical hardware. This means faster development and fewer hardware bottlenecks. And finally, devices like Raspberry Pi and BeagleBone aren't just affordable, they're also incredibly flexible for real-world deployment and experimentation. So whether you're building for smart agriculture, robotics, or industrial systems, this end-to-end process gives you a complete dependable foundation. That's the power of combining toolchains, QEMU, and target boards in embedded Linux development. Got any questions or have any thoughts? Or are you interested in building embedded Linux workflows? Please leave a comment below, or you can drop us an email at info@krishworkstech.com. We'd love to hear from you. Thank you for watching.